Hello everybody, in this lecture we will be solving 1999 IMO problem number 1. Here is a view of this problem. Determine all finite sets S of at least 3 points in the plane which satisfy the following condition. Namely, the condition is that for any two distinct points A and B in S, the perpendicular bisector of the line segment AB is an axis of symmetry for S. I claim that if this condition is satisfied, then S is simply the set of vertices of a regular regular polygon. In fact, the statement is an if and only if statement. It is clear that if S is the set of vertices of a regular polygon, that this condition will definitely hold, right? For example, if you have a pentagon, a regular pentagon, and you just pick two vertices. Let's say the vertices are A, B, C, D, E. If let's say that you decide to pick vertices E and B, and so you connect these EB and you find the perpendicular bisector, which is this line here. You reflect it, so E will move to B, B will move to E, D will move to C, C will go to D, and A will go to itself. So therefore, sure enough, this is an axis of symmetry. The result will not change if you pick two other points. So for instance, if instead of picking the 2 points EB, if you instead picked BD, right? So it won't matter. So B and D will map onto each other. So this is equivalent. Or for instance, if you instead, I should probably say that's more relevant. There you go. Okay, if instead I pick 2 points, let's say BC, the perpendicular bisector would be going through the point E here, a 90-degree angle. So as a result, E would remain, B and C will switch, A and D will switch, but eventually this is an axis of symmetry because the numbering of the vertices doesn't matter. All that matters is the shape. And this won't change if you just pick a hexagon, for example, and you just pick any two vertices and you just reflect it across the perpendicular bisector, which is this line. This vertex is mapped onto itself. These two will switch, these two will switch, this one will remain the same. So therefore the result holds. So therefore the converse is obvious. So therefore finally we need to establish that if this condition holds, it must be the case that S is the set of vertices of a regular polygon. So I will do it in 3 steps. In the first step, let me first consider the convex hull W, which contains, our set S is a subset of W. So W is a convex hull. It is convex hull meaning it is the smallest convex polygon. So W is smallest convex polygon containing the points of S. So as a result, so for instance, if S is a bunch of points like this, so then the convex hull would simply be these points, the outmost, this convex shape which covers the whole thing, right? So this would be the convex hull of these points. So what's interesting is that the convex hull, the vertices of the convex hull will be precisely the vertices, the points of S, right? So it's a subset of S, right? So note that the vertices of the vertices of W are points from the set S, not necessarily the whole set S, but points from the set. In fact, we will just show in a few minutes that it contains all the points, and there can't be any points inside, like we saw here. So the first thing I would like to show is that I claim the first result that I would like to show, I claim that all sides of W have equal length. So these sides measure the same. And for that, we can simply consider two adjacent sides for the proof. So let's assume that, assume to the contrary that we have two adjacent sides, namely AB and say BC, which have different lengths. AB not equal to BC. So we have AB and BC, different lengths, A, B, C, and then so you have some other points, but so this is your convex hull, but these two have different lengths, basically. So if I take simply the perpendicular bisector, say of AC, the perpendicular bisector will definitely not go through the point B, right? And as a result, when I reflect these points, obviously A and C will reflect onto each other, which is good. However, B will reflect onto a point B prime which is not on the convex hull, right? So which is not a vertex of the convex hull. But this is a clear violation of the condition that we have, which namely states clearly that is an axis of symmetry, suggesting that B prime was supposed to be on W, right, by the definition of W here, the convex hull. So as a result, this is a contradiction. So therefore, it implies that the claim is sustained, and all the lengths of this convex hull should have equal length. Now, in the second step, I claim that not only all the lengths are equal, but all the angles are equal. All angles are equal for W. So therefore, W is a regular. Therefore W is a regular polygon. That's my claim. But let's establish this angle relationship. So let's assume again two adjacent angles, namely ABC, angle ABC and BCD. So ABC, so we have already established the side lengths are equal. So let me try to make it look like equal. And then, I don't know, D here. And you have A, B, B, C, C, D. Let's put D somewhere here so that it looks like the two angles are not really equal. So I know the side lengths are equal. However, let's assume that angle ABC, assume to the contrary that the angles don't agree, and as a result I would like to show a contradiction that would violate again the definition or at least definition of W. Assume to the contrary that angle ABC is greater than angle BCD. But then this time, if I focus on the perpendicular bisector of say BC, the perpendicular bisector so will definitely switch B and C, which is good. However, it will not switch A and D, right? Because the shape is not symmetric with respect to the perpendicular bisector of BC, right? Does everyone see that? So if I reflect A, let's call it A prime, because the angle is larger, it would reflect onto a point somewhere here, which is definitely not equal to D. So A prime is not equal to D. But again, this contradicts the definition of W, so it falls outside W, right? But this is a contradiction because it violates the condition of the problem, and as a result, we sustain that all the angles of W are equal as well. Now, final step, step 3, show that there exist no points inside W. And claim there exists no point of S inside of W. So all the points of S are on the boundary of W. Again, let's assume to the contrary that there exists a point P. There exists let's write that down. Assume to the contrary that there exists a point P in S which is inside W, lying inside W. And now the proof is simple. So we have a perfectly symmetric shape. Let's draw the circumcircle of this regular polygon. So we have a regular polygon W, and so something like this with a bunch of vertices, and consider this point say P anywhere inside. Let's call it P. Now pick any vertex here in this shape. Let's say yeah, so let's call this point here as A, and now let's draw the perpendicular bisector of this. Well, the perpendicular bisector will definitely do not contain the circumcenter of the circumcircle, the circumcenter of this W, right, the regular polygon, right? For it to contain the circumcenter, P has to be on the boundary, right? So therefore it will definitely not go through the circumcenter O. But because it does not go through the circumcenter O, it means that there exists a point on this major arc which does not contain A. So there are two. So this perpendicular bisector splits the set W, the convex hull, into two portions, one smaller and one larger. On the larger portion there will definitely exist a point, say point B, such that when we reflect it across this perpendicular bisector, it will fall outside. It will fall, and so this distance is equal to this distance. It will fall outside the convex hull, but again this is a violation of the condition, right? We assumed that all these reflections should end up on the set S. So this is a contradiction. So we ended up outside S or outside W, doesn't matter. W is contains S. So it lies outside W, suggesting it is outside S as well. And as a result, again, we found a desired contradiction. This can't happen, so we can't have any points inside the convex hull. So therefore, the convex hull is exactly equal to the set itself. So the set is a convex, it's a convex, yes, but regular polygon with any number of vertices. At least n is greater than or equal to 3. The number of vertices should be greater than or equal to 3, and that solves the problem. So we have established a proof of this claim that the set S that satisfy this condition is the set of vertices of a regular polygon. I hope you enjoyed the video, and looking forward to see you guys in our next lecture.